Hi, so today we will be looking at, in our textbook, Chapter 5, Section 3, and talking about enthalpy. So enthalpy is a property of a chemical reaction, and we've been talking about enthalpy even last year when we talked about reactions being exothermic or endothermic. We said, well, enthalpy is lost or gained. And we did calculations when we did bonds broken minus bonds formed. We were calculating enthalpy. And we last year just kind of breezed over like enthalpy. It's pretty much heat. It's this kind of the same as energy. Just very non-committal about what exactly enthalpy is. But now we need to get into the nitty-gritty of it. But at the end of the day, in all honesty, the derivation, so what we're going to talk about for maybe the next 3-4 minutes, isn't really important. What is important is how we then use enthalpy, which is, the next few sections. So the important thing here is that we're going to talk about constant pressure systems. And so that the saying that we're talking about systems at constant pressure is important because things change when it is in a completely sealed container and pressure is allowed to build up. So first of all, this is talking about mixing two chemicals out in the open, or a system like this over to the right where, because this piston is able to move, the pressure in the system will stay the same. The volume will change, but the pressure will stay the same. So if you look at this is a little piece of zinc, and here's hydrochloric acid, and then you turn that, and the zinc goes into the hydrochloric acid, and it makes hydrogen gas. The hydrogen gas starts to, fill this tube, and because the gas takes up more volume, the piston will move up. If there wasn't a movable piston in there, then the pressure would have built up. So that's sort of how we get, how we're sort of saying this is a constant pressure system. So what is the definition of enthalpy? Enthalpy is internal energy, so that E that we've been talking about for a few sections, plus the product of pressure and volume. So here's the formula here, right? Enthalpy is equal to energy plus pressure times volume. And what the heck is pressure times volume? Well, that's work. Pressure times a change in volume means that work is being done by the system, which is why it's negative there. So now, and again, this is going to be like a little derivation here that you do not need to know. Just sort of listen and see if you can follow along. So here's that formula from the previous page. H equals E plus PV. Then, so let's talk about the change in enthalpy. So the change in enthalpy, so delta on one side, it would be the change in everything else, right? The change in energy plus PV. So sort of distribute that delta, right? Right? And that means delta H, so this idea of enthalpy, is equal to the change in energy plus pressure times a change in volume, because remember, pressure is staying the same. So the change is going to come from a change in volume. But right? A couple sections ago, we learned that delta E equals Q plus W. So now let's substitute in, right? Instead of, see how this equation is the same as that, except we've substituted for delta E, we've substituted Q plus W. Now you see it's Q sub P. That means constant pressure. That's what that sub P means. So delta H equals Q, which is that energy in the form of heat, right? Plus W plus P delta V. But didn't we say that work was, here we go there. Work is negative PV. So isn't that really going to be canceling those two out? And so therefore, and this is really what the main point that we're trying to get across here is delta H is equal to the heat lost or gained if the system is at a constant pressure, which it's going to be almost all of the time. So therefore, Q and delta H are really interchangeable. And you will see that that we kind of use them back and forth. So some tables will say the values of Q, or formulas will say Q, and we'll just substitute in delta H. And that's totally fine. So now we go, oh, enthalpy. So this is that delta H, is that heat energy that we've been talking about since last year. Endothermic reaction is when heat is gained. Delta H is greater than 0. Exothermic, heat is lost, delta H is less than 0. But you see how the whole time it said constant pressure is maintained in the system, because if not, then we're not really calculating, or then we're not really talking about delta H. We would have to be talking about something else. Delta H and Q are only the same when there is a constant pressure. So this is, you could have done this problem last year probably. Indicate the sign of the enthalpy change. So delta H, positive or negative. It's carried out under atmospheric pressure, and whether it's endothermic or exothermic. So an ice cube melts. So if an ice cube is melting, that must mean that it is absorbing the energy, because melting is going from solid to liquid, right? So those particles must have more energy to overcome the hydrogen bonds that's holding them together. So if it gains energy, then delta H was positive, and that means that it's endothermic. 1 gram of butane is combusted in sufficient oxygen to give the complete combustion of CO2 and H2O. So combusted, we know that that means it's a reaction with oxygen. If it's a hydrocarbon that is being combusted, it will always make CO2 and H2O. And these reactions are always exothermic. They release a lot of energy. So of course, delta H would be negative, and it's exothermic. And the last practice exercise here says a chemical reaction that gives off heat to its surroundings is said to be blank and has a blank value of delta H. So gives off heat to its surroundings. Think of it, would this feel hot or feel cold? And it would feel hot. And so we know reactions that feel hot are, of course, exothermic. So I can cross those off. And exothermic is a delta H of less than 0, because it's giving off energy. So that's just the start of talking about enthalpy and just differentiating it between Q and delta E. But from now on, we're just really going to focus on enthalpy for the rest of this unit.